My name is Vicentiu, and today I'm going to try and give you a very pragmatic approach on how to use common table expressions and window functions. So common table expressions and window functions are a new feature in MariaDB 10.2. They are also in MySQL 8.0, at least the common table expressions are. Window functions are announced to be released in future versions, but I'm going to use MariaDB as a benchmark example now, and hopefully we're going to get some MySQL data next time. So we're going to go through just the regular type of CTEs that MariaDB supports. I'm going to also go into window functions. These two features go well hand in hand, and I'm only going to use practical use cases. These are things that I had to solve at one point to show you exactly how you can get very good performance out of these features. So please interrupt me whenever something is unclear. I have enough time, and this is supposed to be an interactive conversation. I don't want to just speak for 50 minutes without any feedback from the audience. So please feel free to interrupt. So CTEs are very similar to what MySQL and MariaDB now call derived tables. They are basically subqueries in the from clause, just reordered to be on top instead of in the from part. So here we have a CTE. What's highlighted in red is part of the CTE definition. And in the from clause, we have the name of it mentioned. CTEs start with the keyword with, so you're going to always find this when you define the CTE. The name, whenever you want to reference the CTE, you're going to use the name. Yes, question? I'm going to get into that. Okay. And here's the body. So basically, that table, it's kind of like a temporary table, but it's local to this query only. That's what the common table expression is going to contain. All the employees that are engineers in this company. And here we are actually using the CTE. Now, compare that to a subquery, a derived table. It's the exact same thing. Result-wise, it's the same row set, just different ways to express the same thing. Yes, this will produce the exact query plan. So CTEs in this use case are identical to derived tables, but they may produce better query plans later. Here's where CTEs do shine. You can reference them in subsequent CTEs. So first we've selected engineers, and then we have selected only engineers in Europe. And this is done by referencing the engineers CTE. Okay, so instead of having it a recursive kind of view, you get it into a very linear, easy to follow query. Here, actually, you may get better performance from CTEs, but this will probably optimize itself to be identical. I'm going to get into all of the optimizations that we support, and that's where you're going to see how CTEs are useful. Another interesting part is that you do not have to repeat the subquery. So here is where query plans will differ. Because here, if we support CTE reuse, more into that later, you're going to be able to reference the table, to store the table only once in a temporary table and reference it twice. Okay, so you don't have to rewrite the query twice. So in summary, we identify CTEs with the with clause, and they are similar to derived tables. However, they can provide cleaner code, and they allow the optimizer to perform some interesting optimizations. So one, which is probably on everyone's mind right now, is how we are going to reuse CTEs. But first, let's talk about the basic algorithm to support CTEs. So you take the definition, you put it into a temporary table, and for each reference of it, you do the same thing. So the basic algorithm would create two temporary tables with the same contents, and you would just join them together, like regular tables in a database. But this is obviously not the most efficient way. You can reuse it in this case. So we can materialize the table only once, and this would effectively provide you double the speedup just by using CTEs. On the other hand, when you try to reuse CTEs, you cannot perform other optimizations on them. So there is a trade-off. Either you choose to reuse CTEs or you choose to do other optimizations. Another one, which is very common when you use views, go ahead. This is local to this query only. So it's a temporary table for that query. It disappears once it's done. So the other optimization, this is something we already do for views and derived tables, but now this is also apparent in CTEs, is you can do merging. So here, when you have a CTE that is used in a join, but you do not have any group by clauses, then you can actually take the definition of the CTE and place it in the query itself. Okay, so we're just moving stuff around to get the same result, but now the optimizer actually has the full picture of the query. So the optimizer now is free to choose the best query plan that it can find. Okay, so this is actually a direct definition of syntactic sugar. We are rewriting the query to have a better picture for the optimizer. As I've said, this is similar to how we do views. Now, the further optimization, and this is something very interesting, and this is unique to MariaDB right now. We actually had this contributed by an outside contributor. It was actually a student, so this was a very interesting project. You can actually make use of conditions that are in part of CTEs. So here's the problem. When the CTE has a group by, merging is no longer possible. When you push the group by into the query itself, you modify the result set, because now you're grouping instead of not grouping. However, if you have conditions in the where clause, maybe it makes sense to first filter the CTE before actually producing the final result set. So instead of computing one giant temporary table, we filter only 2 years from our database. So we move the condition from the outer query into the CTE. So this is called condition push down. Looking at the text, it's actually moving up, but it's pushed down into the CTE. And this makes things go faster because you are storing less data in the temporary table. You're basically filtering out all that's not interesting in the CTE and getting only the interesting data. So let's compare to other database vendors on this. We've tried to look at how major database vendors support this feature. So here's a comparison to Postgres, MySQL, and SQL Server. So we've used SQL Server quite a lot to see how to deal with these optimizations. So MariaDB does support merging. It's similar to views. And MariaDB does support this condition pushdown. However, we do not do CTE reuse at the moment because we have not yet decided how to balance between making use of reuse and making use of condition pushdown. Because if you're reusing, you cannot do any of the other optimizations. So you need to find a way to decide on this. We have not found a good solution yet, but this is coming. This is probably going to be in the next release. People are working on it right now. SQL Server does not do CTE reuse as far as we could figure out. We are not Microsoft engineers, so we don't know for certain, but this is what we could figure out so far. Postgres has a very different approach in that they consider CTEs to be optimization barriers, so nothing can be optimized using a CTE. It's just optimization inside the CTE itself or the outer query, but nothing goes between CTEs and the outer query. So SQLite does support CTEs, but I do not know exactly which optimizations they support. Yeah, right. Oh. I would be very interested in knowing about these. Okay. Okay, and obviously MySQL does merging. This is pretty easy to do considering how the architecture of the server is. But they do reuse and do not support condition pushdown. So this is one of the interesting things that I know that MySQL is also going to work on this, but I have no obvious fixed dates on that. Okay, so now that we're done with CTEs, let's see how much time there I have. Oh, plenty of time. Any more questions on CTEs so far? I'm not talking about recursive because it's a lot of information already in the slides, so I've postponed that. But indeed, recursive CTEs are supported by MariaDB, and the interesting fact is that they make the SQL language Turing complete. So you can actually write any program in SQL if you choose to do so. It's not easy, but you can do it. Okay, so now let's move on to window functions. Now, window functions are a very strange topic, especially when I talk to people. They don't really understand how they work, and it's very hard to explain to them how they work and how they should think about them. So this is what I'm trying to show you today. I want you to get a good understanding of how to use window functions. So the trick about them is that they are able to access rows from the same table whilst computing a value for a certain row. So say you have this huge table, the blue result can depend on the green row there. And this can only be done with window functions aside from doing self-joins. So if you want to compute something on multiple rows from the same table, your only other alternative is to do a self-join. So you join the table with itself and get the combination to perform the computation afterwards. But since window functions allow you to do this, it can eliminate that expensive self-join, and you can get queries which take 10 hours or more and shrink that down to 1 minute. So this is what we're going for today, and I actually have an exact example that does just this. All right, so window functions are similar to both regular functions and aggregate functions. On one hand, they produce a result computed on a set of rows, like aggregate functions. So think of sum. Sum is computed over a result set. But at the same time, you get one result per row in the final query. So instead of collapsing everything, window functions do not. So they behave like regular functions in this sense. So you can identify window functions using the over clause. This is a mandatory syntax. So I'm going to start with a simple example of a window function which behaves more like a regular function. You have this table here with users. They have an email, first name, last name, and we separate them in admins or regular users. Row number is a window function. You cannot have it as a regular function, so you need to use the over clause. And what it does is it just outputs a continuously increasing number as you go through the rows. Okay, notice the over clause there and the empty brackets right after it. That's important. Why is it important? Well, the first thing is that think of window function computation as the final step in getting your result. So first we get all this black stuff here. So this table is computed, and then at the end, we add this final column. Okay? And this final column, the results for it obviously depend on the order of the rows that come in here. And since if we do not specify an order, you can get that result, but you can also get 2, 1, 3, 5, 4, as well as a reverse one. Okay. So how do we get a stable result out of this? Well, we can make window functions force an order, but this is not the final order of our result. It's just for that window function. So the window function now gets the orders from the table in alphabetical order by email. Okay, so now this email, admin, will always have number 1 because it starts with A. But the final result that you will get here is not necessarily ordered by email unless you specify order by email in the outer query here. Okay, so this order by is important. Make sense? People are, I see you looking very strange at this slide. Is there something unclear?
Oh, no, I was just checking to see if the number was actually specific to Windows function or whether it was I already looked it up on.
Yeah, so you cannot use row number as a regular function. And another thing is that we may want to group these users. So we may want to have an increasing number, but one for admins and one for regular users. And we can do this with another syntactic clause, partition by. So now we're just splitting the data by account type. So you can think of this now as 2 different tables, one with only admins and one with regular users. And the result is computed independently for each one. Oh, by the way, the slides are on the Percona site, so if you want, you can look at them there as well. So there's no need to try and remember this. Okay, and now let's look at how window functions look like aggregate functions. Now, window functions compute results on multiple rows. Actually, let me start with this. Let me describe the example first. So here we have a sensor which picks up data and it logs it into a table, and you get a lot of values, and the values are pretty noisy. Okay, we can see that the line is not actually really smooth, but we would like to smooth that out. And we can smooth this out using the average function, but used as a window function instead. So here we take the time and value, and we average the value. First, we order the results by time, because we're still interested in them in the chronological order. But we also tell the average function to take 3 rows before the current row and 3 rows after. So it's averaging over 7 values in total. Okay? We can change how this averaging works by increasing the frame size. So now we're averaging over 13 values in total. Obviously, the line is going to be smoother, but we're going to have a bit more information loss because we're averaging over multiple values. To give you a more clear picture of how frames work, this is the same example. Instead of average, I'm using sum so that we do not divide by the number of rows in the result. In blue, I've highlighted the frame size. So all the rows in blue are part of the computation. The red row is the one that we're computing right now. And in parentheses, you actually have the mathematical formula for the result. So here we have these 2 rows added together. And here we have these 3 rows added together. Notice the difference in frame size. So it's 2 rows following and 1 row following over there. Moving on to the next one. I'm sorry. Okay, so moving on to the next one. The current row has moved one element. The frame advances. We keep the previous row. However, if we move one more, we start discarding rows from the top. So here, we've lost the value 2. And we have only added the value 4. Okay, notice how for each computation, we subtract a few rows and add a few rows. And this is important because window functions can do this trick. That's why they are actually computed in constant time for each row in this in this sequence. Most window functions can do that, except for a few. If we move on one more step, we see that we begin losing rows from the other example as well. Like I've said, every new row adds one value and removes one value. Again, sorry? No, it's actually computing a sum over 2. It's basically adding things as it starts seeing them. And it's removing them as they start to disappear. For example, for count, it would count them as 2 here. Nulls do affect count if they exist somewhere around here. So if you have count here, and you count, say, value, that will only give you 1. I had a question on this example before, if you can actually filter out rows which do not have the full frame. So can you somehow filter out this top row and this bottom row here? And this is not possible with standard SQL language. You need to filter out in a subquery afterwards. Okay, I mentioned about this. And now this is how the final result would look like. Yes? You can use any aggregate function as a window function. You can use expressions here. So you can make sum of something minus sum of other things, but you cannot. There's limited ways on how to define the frame. So there's an extra way to define frames. There's range. So instead of rows, there's a range frame definition. I don't go into details about this here, but you can think of it like, instead of saying 1 row after, say 1 day after. Okay? And it looks at the value of the current row column that you're ordering by, and then it takes more rows there. It's something a bit more hard to understand, but if you're interested, you can look at the documentation. It's explained there with a few examples. Okay, so now I'm going to start with 3 practical examples. And these are going to have both a regular SQL, how you can do them with normal non-analytical specialized functions, and with window functions. So here we have a set of bank transactions, and one thing that you would like to have, I know that my bank has it, you get an account statement, account balance after each transaction. So when I buy something, I get a negative amount in my account. When I get money, I get a positive amount added to my account. And I would like to know the exact amount after each transaction. We obviously store multiple customers in our bank, so we have both multiple customers, but we want to do this for all customers in this case. Let's see how we would do this with regular SQL. This is a bit tricky to think about. So we can use a subquery. For each row that we are computing, we sum up everything that's before it. So we look at the rows that belong to the same customer here, and all the transactions which are before our current transaction, we add them together. Okay? And these will represent the balance for that transaction. However, is this the most intuitive way how we can write it? Let's see how this looks with window functions instead. Well, we want to sum our transactions. We want to separate our data by customer. So we're partitioning by customer. We want our data to be in order by time. And then we want to add all the rows from the start of time, unbounded preceding, and up until the current transaction. Okay? Does this look clearer in this case? Let's see how performance affects. So look at the regular example. No indexes, nothing, just the query optimizer trying to do its best without any extra information. The time increases basically linearly, but the constant is quite large. If you use an index, then this can be divided by a factor of 10, but you do incur a bit of penalty when you use window functions for small rows, for small sets. So look at this example here. So the second line here shows you the overhead between window function computation and using an index. However, because you're not doing this self-join each time, this will be twice as fast in this example. Okay? Another frequent example is a top-N query. So you want to get the top five earners in our company. We have two departments here. The numbers for the salaries are not representative. It's just to show you the difference. One uses only 3 digits, one uses 4 digits. Okay, no correlation whatsoever. To do this with regular SQL, you have to filter out elements. So in order to filter out, to know exactly what we need to filter out, we need to count the number of people who earn more than us. And in order to count that, we need to do a subquery in the where clause. Okay, this is not so pretty, because if we also want to get a number for our employees, for example, want to rank them from increasing 1 to 5, we have to repeat the query. Okay, it's basically the same thing. We just need to add it to the select clause as well. With window functions, however, we can do this a lot easier. We have a specialized window function called rank, and we partition all our data by department and by salary. We ordered it by salary. We ordered it descendingly so that we get the top 5 people. But now we do not have the top 5. We actually have all of them, and they have the rank. If we want to filter this out, doing this doesn't work. So you cannot do where on a window function. Because like I mentioned, window functions are computed after this part is done. So you cannot filter out here. To do this, we make use of the first feature we discussed about. So we can wrap this into a CTE and then filter out the CTE afterwards. Performance here is a lot different. With regular SQL, this will not even finish, at least not until we need to get back to where we came from. And with window functions, this is almost instant, because it's just one scan through the table. And that's it. 20 million rows, no problem. And the final example is with a set of machines. This is actually something that I had to deal with. So we have a set of machines. They require servicing, and they get service at certain intervals. When that happens, they get logged into a table. We want to know what is the average time between services for these machines, so that we know if there is any machine which frequently does not get serviced. Here's how the data looks like. It's just time and which machine was serviced at that particular moment in time. And we want to get the consecutive differences between 2 services for each machine. Okay, so for machine ID 5879, we want to get each pair of consecutive rows. Doing this without window functions is complicated. You need to first join the table with itself, so that you can actually look at pairs of rows. And then you need to first group the rows by machine ID. So here's the equality operator. And then you need to select only the timestamps which are before your current service. After that, you need to make sure that you select the most recent service that is not the current service. This is done with the max function here. And then we get the time difference. This is complicated. I'm not going to go into more details on this. But let's look at how window function makes you write a very simple query. There's this window function called lag that all it does is it fetches a row which is one row before the current one. So here we just partition all the data by machine ID, and we order it by time. We just tell it to look at the previous time. So lag of time is the previous moment of service. Performance-wise here, these are interesting numbers. So let's have a look here. There's a typo here. There should be one. Yeah, I think I added an extra one here, fortunately. Okay, so this should be 224.5.15. With regular SQL, this will not finish at 10 million rows. With an index, it cannot use both columns to index, so only one would be used, which is machine ID. This still takes a long time, and with window functions, this can be done almost instantaneous. At 100 million rows, this takes about 5 minutes. So in summary, window functions help you eliminate expensive subqueries. And as you've seen, window functions can make queries a lot more readable. And at the same time, if you make correct use of them, they can make your queries faster. So which functions do we support? For MariaDB, we support all the standard window functions: row number, rank, dense rank, percent rank, cumulative distribution, and n-tile. N-tile is one of the is useful to compute the median. Although there is a median window function, we do not support it yet. The only problem is with group concat, which is a special function. Due to overflow bugs, we've not implemented it as window function yet. And the first value, last value, and nth value are also supported. Go ahead.
Something like lead and lag function, customize how many rows?
Yes, so lead and lag also take a second parameter, and that's the number of rows. It's interesting that it also takes a column as a parameter, not just a fixed number. So you can lead or lag dynamically based on your data. So it's interesting. There is a difference between lead and lag and nth value, first value, and last value. So nth value, first value, and last value work, and they are aware of the frame definition. Lead and lag are not. They look at the current row, they look at n rows before or after, regardless of what frame you define. Yeah. And this is something that we plan to do. So all of these are in our plan. We do not support range frames with time intervals yet. It's easy to do, we just did not have enough time to do it. The distinct clause is hard to get right performance-wise, so that's why we do not have it. Group concat I've mentioned already. And there's more window functions, which are usually, I think, 1 day of work for each. It's coming eventually. All right, so this is all I've got. I thank you for paying attention. I will also post a blog post about this soon. If there's any more questions, I'm available. Thank you.